All right, we'll get going here in just a second. I gotta flip over here.
We'll note that the winter storm watch has now turned into a winter storm warning.
So we were just watching it, now it's a warning. When is it actually a storm?
Is it getting bad or is it getting better?
Worse.
It's getting worse.
Or they're confirming that we actually get the snow, right? So weather, Department of Michigan, what do we get here?
I've heard things as high as like 20 inches, but most like official sources I've looked at have just said like 12-ish.
I don't know. Is there like amount of snow? Why am I not seeing like a total snow?
I use the AccuWeather. That's the second one, I think.
It's froze on me. AccuWeather. Let's see what it says. 12 to 18 inches of snow, Wednesday through Thursday evening. Oh, so that's like all day long. So they'll tell us officially if campus is closed or not over emails and alerts and whatnot, but apparently not everyone signs up for alerts. If the campus is closed, I can just still do this from home on Twitch. I think is okay for a plan. If that doesn't work, then just shoot me a message and say you couldn't make it, and you can just watch the recording if that's okay. I mean, that's always an option for you anyway. So, but probably we won't be here. I think we'll see how that goes. I don't know. We'll see. So I'm glad we were able to get the lab in today at least. So, all right, a couple things today. Then we have upcoming. Project Zero, due Thursday. All right, so the first thing we're going to do Thursday is talk about Project Zero. I'll go over my solution for it. I know I talked with a couple people today after lab or during lab. A couple questions here. So a couple things to note, right? Including the UML class diagrams. So that was just the little picture. It's the 3-box. Top is the name of the class, middle is all the attributes, and bottom is all the methods. So you can just do those real quick in Word. You don't need a fancy program like Visio. They're not too hard to do. Now, this is like the minimum design. You are welcome to expand and change upon this. Right? I'm not hard and fixed and fast that it must look exactly like this. You can add other methods. You can move methods around. You can override things wherever you want. Anyway, you think will get the job done. I'm fine with. A couple other interesting things here for repair ships. If you'd like, a repair ship can repair a blown-up ship with 0 health. If you'd like, it could also not repair a blown-up ship at 0 health and say that's just unrepairable. That is an option. It's ambiguous here on purpose. Totally up to you. So whatever you think makes more sense for the game here. Again, that's something that would be clarified with whoever came up with the requirements, but not too big of a deal one way or the other. And then unit tests for 100% code coverage. This is, we're eyeballing it here, where we're not actually using any tools for measuring. But so if you have a function, there should be a unit test that makes sure that that function runs. If there's a block that has an if and an else, right, one of the tests should make sure the if runs, one of the tests should make sure the else runs. That's what we're talking about for 100% code coverage, is that all of the code should be executed during our tests. Now, that doesn't mean that you need to test the init method here 50 different times. That's not what 100% code coverage is. It means that the code is run during one of the tests. Right? If you test init once, I'm fine with that. You don't need to test it over and over and over and over and over again. Because Battleship derives from ship. If there's something special you want to test, like, hey, do I have the number of torpedoes correct? Go for it. That makes sense. If cruiser doesn't do anything special with init, you don't need to test its init. Okay? If you want to test the cruiser gets the correct range, health, and attack power, sure, that could make sense. Right? When I make a cruiser, we're getting the correct values here. Right? But you don't need to repeat, hey, is the X in the right location? Is the Y in the right location? Is the alignment correct? All those things. Just test what's specific to Corvette, that you get the range, health, and attack power. Right? That's what we want to focus on for that. The other things, don't worry about. So for these moves, these are probably things you want to override. Other option for overriding it is you could pass values to ship to say, hey, this is your vector that you move on. Right? And then it can actually do a move here, because a ship all by itself has no vector for moving. move on a base class ship does nothing unless you go through and give it some sort of values of what it should move at, and then you can pass those through, or you can override them. Right? Either approach will get the job done, whether or not you're overriding the move method, or you're just passing when you construct it, hey, I want you to have a movement vector, and every time you move along that vector. Both ways will get the job done. For status, that name is just the type again. Is that really a repeat? I think it is a repeat here. Name. No, I'm sorry. So name here in this case, you can name your ship. Right? So you could call them TIE fighters, X-Wings, if you wanted to be derivative and, copy off of Star Wars. If you'd rather copy off of Star Trek, right, you can name them the USS Enterprise or Klingon Birds of Prey, those sorts of things. Right? And the Enum, we got to talk about Enum today. So Enum just gives us a nice way of putting names to values, so we don't have to pass around like a 1, a 2, and a 3 that have magic meanings here. Enums let us put class names to those sorts of things, and then they're actually stored really efficiently behind the scenes. If you store something as a string, right, it has to take up a string's worth of memory. If you just store a single integer, it takes up 4 bytes. It's relatively minuscule for storing. And again, for our purposes, we don't really care. We're not going to have millions and millions of ships. But if someone wanted to take this game and turn it into like No Man's Sky and scale it out to millions of people around the world, I don't ever think a million people ever played the game, but you probably want to have a better way of storing those sorts of things. So let's fire up a little example for enums here. Just do a new project. I don't know. How about enum examples? Why not? So, and again, I always just go Google it because I can never remember. Like on Enum, there's a class that you inherit from in the Python library. See if we can get our answer here. The Enum class. So you can create an Enum by inheriting from Enum, and then you just assign your attributes particular values. And they can really be anything, but int's going to be the easiest for you here. And then you can name them here. So usually we'll use all uppercase. They're essentially like static values. Very similar to what we did with the number of jumps or the possible moves. We said it's a class level, all uppercase. That's essentially what we'll call a static value. It belongs to the class level. But Enum makes them even easier for storage behind the scenes. A little bit more efficient here. So when I inherit from Enum, right, so from Enum import Enum or something. Is it uppercase, lowercase? Never remember the casing here. Yeah, lowercase enum is the package, uppercase enum is the class, and then we'll say class. I don't know. I like the. How about light? And we'll say inherits from enum. And then there's no inits or anything. All you just do is write in there, assign name and associated value. So if we wanted to play a game like red light, green light, we could have red is 1 and green is 2. So then somewhere else in our script then, if we want to use these here, we can play our game and print, let's play red light, green light, sure. And then you can use these particular values, right? We can say, hey, if light.red equals, I don't know, have some sort of random value and have their input and pick a red light or a green light. But you can access them by class name dot value. So light.red will mean something here, and you can compare it to something else. So if we wanted a random value, I don't know, should we add a yellow? Well, why not add a yellow? I guess that's not really how you play the game, but it's okay. Red light, yellow light, green light or something. It's been a while since I played the game. So we'll pick a random number. So we'll pick a random value is random from import random dot and int. We'll do 1 to 3, and then if my random value is equal to 1, then I can go assign a current light. Current. We'll do it this way. So if the random value is 1, we can say my current light is equal to light.red. Well, if My random value is 2. My current light will equal light.yellow. And elif, my random value is 3. My current light will equal light.red. Oh, green, sorry. And then we can say, hey, if my current light is equal to light.green, I can go do something here. So the comparisons then are really easy. I should probably spell that better. Current and current. If it's green, then we can print go. Right, that sort of thing, and do some sort of comparisons with the name of the attribute. So the advantage here is I don't need to pass around 1, 2, and 3 in my code and have to remember what 1, 2, and 3 mean. I can just say, okay, I know this is a yellow light. Or, for my self-driving module, if you see a yellow light, you have to gun it because you've got to clear that intersection, right? Nobody ever stops for yellows. You just go. Just go, go, go. Sure, whatever you want to do here. But you can compare them really nicely here with your attribute compared to the class dot value here. And then behind the scenes, they're going to store really nice and cleanly as integer values rather than string values. So if I have millions of these things in my database or in my application somewhere, I'm tracking all of the lights everywhere to tell my smart cars where they should go, when they should stop, that sort of thing. They're going to store very nicely in memory as these integer values really cleanly. That's the big advantage. So mainly for the name. And then if you actually use the Enum class, we can assign them values here this way. If you just make them as static attributes, they don't work quite as nicely behind the scenes. Enums is a little bit cleaner. So it should work out pretty nice. So you can use enums for those. Does that make sense? Yeah, Casey was asking about that, and I forgot to talk about those before. So that's our enum example. You just play around with them. Again, everything's about putting a name to values. If you just have a number somewhere randomly in your code without a variable, like describing it, it's called a magic number, and it's considered bad form. Because maybe we'll remember what it means, maybe we won't. So always a fan of putting variable names to things. So this is kind of the canonical way of doing that. If you've got, hey, this is an enumerated list of things, right? Enum for enumeration or enumerated. I have a fixed number of these things. Here's the possible things that you can pick from. It works out pretty well. And then you can even iterate over these as well too. Like you can do a loop for value in the light class. You can get these things out. In our case, we don't really need to loop over them, but you could do those sorts of loops. And I think, was it light? You can say light.green. You can get out the value and the name. So you can get the name itself out, and you can get the value behind the scenes out as well. So later on when we do something with cards, using enums here is kind of nice because you can use those associated values, or you can use the names when you're printing them out. So a couple other advantages we'll come back to later when we go. Okay. Hey, Hector, thank you so much for donating those bits to the Student Scholarship Fund over the University of Michigan Dearborn College of Engineering and Computer Science. Oh, I didn't take a breath first, and it messed me up. Supposed to take a breath first. Okay. That's so cool. We're actually close to another payout, another $100 towards the scholarship fund. I'm really excited. I know this because I had to check it because I got my tax documents. So I get to claim it as income and then claim it as a deduction, which is fun. So, yay.
Does that do anything for you?
I actually end up paying money on it, but it's not very much, so not too big of a deal. So I don't actually know if I'm going to hit the standard deduction limit this year or not. I have to look and see when I actually do my taxes this year. Because they made the standard deduction relatively generous. So I used to have to itemize every time, but now it depends on circumstances. So, all right. So let's talk about array-based sequences. This is lots of fun. So this is array-based sequences. So in Python, we have the built-in list. In other languages, if you come from C++, you might know it as a vector. Other languages just use a base array. So the base array is actually really boring and really obnoxious in other languages because an array is typically a fixed size. We're spoiled in Python that our base array or list here is resizable. You can add to it, you can take away from it. No big deal. Python does all that work for us. So in other languages, not so nice. And you have to use their vector or array list in Java or C#, those sorts of things. Hey, Aiden, thanks for coming along. So one of the things we want to look at is performance of a list. So we don't need to deal with making these things resizable because they're already resizable in Python. So I can make my list, some list, and then I can add to it as much as I want. So for number in range, I don't know, let's do 100. We'll take some list and we can append the number. No big deal. This will make our list 0 to 99 easy. Other languages, you have to tell how many items are going to be inside of it, and you can't add and subtract. Again, we're ignoring that. What we want to look at is performance of a list. So adding something to the end is actually pretty quick. Works out really nice. Lists, however, though, some lists lets you insert an item. So insert says, hey, what do you want to insert and where do you want to put it? So insert says, what is the new index here? So you can insert something, say at index 0, inserts, I don't know, we'll add -1 for fun. This will put a -1 value at index 0. What has to happen behind the scenes then for that is every single value in the list has to get bumped down, 1, 1, 1, 1, 1, moving to make space for that new location here. That's really slow. So inserts are slow at the beginning of lists. So some of the notation, we skipped over that whole chapter on performance notation because most of it we don't care about. One of the things we generally care about is we'll call it the average time. So you say this is O notation or big O notation. So there's a Greek letter for it. I forget what it is. But big O notation, generally what we're going to talk about is our average performance time. So on average, how long does something take? Well, most of that depends on the size of our list. Right? If I have 10 things in the list and I want to put it at the front of the list, I have to move 10 things. Move this one, move this one, move this one, move this one, right, all the way down until I have room to put it at the beginning. So in terms of the time that something takes, it's relative to n. Right? The more n items I have, the longer something takes. So a lot of times we'll talk about things in terms of n. So a O of n speed means the more n I have, the longer it takes, on average. Right? If I add something to the end of the list, if I've got one thing or 10,000 things, it doesn't really care. It's just going to add it to the end of the list. Nothing has to move here. So this is an O of 1 or constant. Right? On average, again, this is average time. We're very specific here. This is average. It's constant. Now, what has to happen behind the scenes is a little bit of magic. And the magic here is what Python takes care of for us with a base list, or in C++, a vector. So when we store a bunch of values here, what we're doing is Python goes out to your operating system and says, hey, I need a block of memory to store something, a bunch of memory. And I don't even remember what Python usually does. I want to say 10, but I don't know that for sure. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 locations, right? So index is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So Python's going to go out and ask for a bunch of memory to store something. And it needs to track how many items we actually are using here, because if it only stored enough space for what you wanted here, right? So if I had 0 items in my list, and then I went to add something, Python would have to say, oh, hey, operating system, I need a place to store one thing. And it would go out and give you a block of memory, enough to store one thing. When you go add another thing, what has to happen is this chunk of memory has to be contiguous. It has to be, here's the start of it, and here's the end of it in one block of memory. The reason is when you use an array or when you use a list, you can say, hey, I want number index of 27. And it has to go find that value, whatever's stored at index 27, instantly. Right? It will go find it immediately. So this is immediate lookups. And the way it does that is it takes the initial location. So when you look at a Python list, it's stored at, say, x27f2. Remember, memory locations use hexadecimal for reasons. The reasons are important later. We don't really care. So some location in memory. Then every next spot is an additional plus, I want to say 64 bits here. because we use 64-bit memory, 64-bit operating system. So every location then is another memory address away. So at 27F2 is the 0th item. At 27F2 plus 64, which is that F, my goodness, how many 16s is that? It's 416, so that's 40 in hex. Again, don't worry about the hex, it doesn't really matter too much, is index 1. At index 27 is 27 times 64 bits. And in hex, however that math works out to be, we'll pretend it's something here, is x27, it would probably be like 29F0 at this point or something. We could do the math if we wanted to. It just says, okay, 27 more of these from 27F2. Go access that location in memory, and here's your 27th index. Boom. It does a quick little arithmetic and finds the item by index, because all of it's in one block of memory. So I can take the starting address, add 27 to that, and now I go have the 27th item. Actually, the 28th item, right? If index 27 will be the 28th item. So because it's a contiguous block of memory, I get instant lookups with a list. They're really fast. I can get any value out instantly by index because it's arithmetic. I have one block of memory. So if I weren't storing things, or if I weren't sized enough to have room, anytime I wanted to add something, you have to go and tell your operating system, hey, I need a new block of memory. And then you have to copy from this one to 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 this one, over and over and over and over and over. It's really slow to do this copy, right? The more n's you have, the more n you have to copy. So if you said, hey, I want room to store 4 things, right? I'm going to store the first thing, the second thing, the third thing, and the fourth thing. And then I want to say, oh, I need to add a 5th thing. To get a contiguous block of memory, your operating system doesn't say, hey, you've got more space over here. You have to go out and ask for a new block of memory at the size that you want. So we say, hey, operating system, I need a new block of memory here so to store my values, 3, and I can throw in a 4. I'd have to copy 0 and 1 and 2 and 3, and these could be any values, right? Then I would have room to add my 4th. So you can see this would be really slow to have to do this copy operation. And if you go through the book, there's actually a way to make Python do this. I don't know why you'd want to. I think that's terribly dull to have to rewrite this sort of thing to make list perform, to make your own list, essentially, where it can go and add to it. So what we do is we do a little bit of magic here. And thanks to math, it turns out if you take some block here, we said, hey, let's size it to 10, and I'm just going to track here. So you can add now 10 things, and I don't have to go out and ask for more memory because I'm going to oversize my storage. So we'll pretend it's 10. I don't actually know what it is. We can go look it up. It's not too bad. We could Google. For our purposes, we don't really care. So I'm going to give you space for 10 things, and I'm going to track your number of items here. So every time you call append, I'm going to increase your number of items. So right now you have 0 items. When you append something, I'll put it here. Let's put, I don't know, 42 in, and I'm going to increase your number of items. Now your number of items is 1. The next location I'm going to write to is that index in my oversized array. Right, so I have a list of size 10. This array base means it's one contiguous space. Right, and then once you add something here, you add a 77. Now you have 2 items. Now the next location is here. So adds now are constant time because I have space for it. On average, I'm usually going to have a space for you. Then the math magic happens. We say, if you run out of space, you add all 10 items here. You add a bunch of values here. Now I have 10 items. I have no index 10. It doesn't exist. I need to now increase my capacity. So the easy way for us to do this, and mathematically way for our average to still be quick, is we're going to double our space. So I'm going to say, okay, I did have 10. Now I'm going to make room for 20. So I'm going to double my space. Now I got room for 20 things out here. I'm going to do a bunch of copies, which is slow, right? I have to copy 10 things. That's slow, but now I have room to add 10 more because I've doubled my space. So what happens here, if you look at the amount of time that it takes, so if we were to say this is the operations here, and this was the number of items, and we kind of graph this out here. So based on the number of items, right, we know that we said when we had 0 items, 1, 2, 3, on and on and on and on. Here we've got 10, here we've got 20, and we'll go double again at 40, right? All of these here then take one operation. Here's one operation, one operation, one operation. If you were to like make a little bar graph here, right? Once we get to 10 though, it's going to take 10 operations because I have to copy those 10 things over into the new array, but now I've got a space. When I get to 20, it takes 20 operations because I have to copy 20 things, and now I have space for 20 more. Right? My graph here is kind of terrible, but what you can imagine here, right, when this gets to 40, it has to do 40 operations. It's even bigger, right? The more n we have, the longer it takes. Thanks to some mathematical magic, if you kind of imagine this 10 here, let's see if we can draw this out better here. Let's say, so this is 0, and here's 10, and here's 20, and here's 30, here's 40. If we do this to a better scale here, right? And this is 1, and here's 10, and here's 20, here's 30, and here's 40, right? So 10 would be at 10, 20 would be at 20, 40 would be at 40, right? You get these little bar graphs, right? All the other ones are nice and flat, but these ones here are a little tall. What you're going to imagine is you're going to take that bar graph and you're going to lay it down. So imagine this 10 here now gets knocked over, and we're going to average out the cost of adding all of those. We're going to, our technical term here is amortize. The amortized cost, I'm probably saying it wrong, amortized, it's a hard word to say because I'm bad at speaking. If we average the cost out across the next bunch of operations here, so for items 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, right? If we were to say the cost of adding a 10 got averaged out across 11, 12, 13, 14, 15, 16, 17 is only 2. It took one operation to do it, plus the averaging out that cost across. Then when we get to 20, knock that one down, right? That gives me, again, a nice little flat. Every operation took 2 operations because we knocked down the cost. We're averaging the cost across the next bunch of adds, right? Knock that tower down, knock that tower down, knock that one down. And it averages out so that every operation now, on average, costs 2. Most of them are 1. Every time we get to a slow point we have to do a copy, we're going to say, oh, well, you know, on average, we can average that out across the rest of them that were really fast. That's the mathematical magic that we do to say, on average, adding something to the end is still a constant operation. On average, because most of the time, it's really fast, it's 1. Some of the times it's really slow, but we'll average that cost across all the ones that were fast. And if you can imagine those big towers, the big spikes laying down, lay them down, right? I think that makes sense that on average, it's still a constant time, right? It's a constant of 2. Because we have that big spike got averaged across all the other ones. Does that make sense? How we can say this is on average, it's a fast operation? Now, some of the performance stuff we skipped. You have a best case performance and you have a worst case performance. Worst case is important, best case is kind of important, but you're rarely ever going to get best case performance. So more important is average case performance. And sometimes you can get the worst case. So if the worst case is really, really, really bad, and you happen to hit that worst case, really, really, really bad performance sucks. Okay? So just keep that in your back pocket. But most of the time we care about this average time. So on average, it'll be constant. Not actually true, but on average it is. Okay? So inserts, though, are always bad because we have to bump so many things down to make room for them. It doesn't matter if we have space at the end because I have to shift all those end things in their location to make room for where I want to put this. So our term here for inserts here, the performance is going to be, it's the n items minus the kth index. Kth index. So if I want it to be at index 0, n items minus index 0 means I have to do n operations. N items minus a kth index of, n minus 2, right? It's almost near the end here. If I want to insert it near the end, I only have to shift like 2 things. So n minus k is 2, it'll take 2 operations. The problem is we don't know what k is. So on average, it's an n operations, right? So the average time is still O of n. We say on average, because we don't know where k happens to be. half the, if you average out where k happens to be, if k is in the middle, like half the operations are near the front, half the operations are near the back, so we say, well, the average is the middle, right? If you think back to your calculus class, right, you learned something about n divided by 2, right? And the sum of n over 2, does that ring any bells for math class? If we were to say, hey, I've got so many operations, I'm sorry, my sugar's low again, darn it. I'm going to need to go get some sugar in a little bit before I get too spacey. Right? If we were to do 1,000 operations, right, and we had to take the first one was at 1, the second one was at 2, the third one. So a lot of them are really slow. We start getting in the middle, and then they start speeding up faster and faster and faster. It's still really slow, right? Even if it's half of n, it's still n-based, right? If I've got 10,000 things, half is still a lot of things, right? If I only have a couple things, if I only have 5 things, sure, half of 5 is fast. It's not very many operations. But it still grows linearly here, even if it's half of n, right? If you were kind of graph out here, Desmos is like the coolest graphing application website ever. I love them. If your math teacher didn't use it, I'm sorry. Let's go to the graphing calculator. Right, again, we don't use n in math land. We use x and y in math land. Sure. So if we just graph x, great. If we graph x over 2, it's still a linear growth, right? The bigger n gets, the bigger this thing gets. It just happens to grow slower. Now, we do a little bit of math hand waving here, a little bit more mathematical magic, and we pretty much say any coefficients go away. Coefficients go away. Because if we're talking about 1,000,000 things, and you have to do 1,000,000 operations, it's still growing n times here. It doesn't really matter that much that you're doing half of that, right? Sure, it's a little bit less, but in terms of growth, you're still growing a linear growth. We're going to throw away the coefficients. They get thrown away, right? Just to simplify things. So what really matters then, the only thing that stays are exponents. So exponents will stay because the growth here of x squared is way, 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 way significantly faster. There's no coefficient here, right? What we care about is how fast the thing grows. On the other hand, if we were to take, like, say, the log of x, we'll keep that because really logs are coefficient or logs are exponents, right? Think back to math class. Hopefully your math teacher drilled it into your head. It's still in my head. Logs are just exponents. They're just fancy exponents, right, on the other side, right? If you imagine that growth curve. So exponents will stay, but any sort of coefficients we're just going to throw away because the growth of that is still either linear or it's exponential or it's logarithmic, like it's a slow exponential, right? That sort of thing. So in terms of things and their speed, right, our crash course in performance here, right, our O of 1 or constant is the fastest. Constant. And because we throw away coefficients, right, any sort of O of 10, O of 100, O of 1,000 is still constant time. It doesn't matter how many n items you have. If you still have to do 1,000 operations for everything, it's still constant. Now, 1 is better than 1,000, yes, but we're going to ignore the coefficients, right? So we'll say O of some sort of log of n is better, or is the next step, right? It matters how many n, but the more n we have, the growth is slow, right? It grows slow in terms of n. Or we can get linear, right? We can have O of just n linear here, some sort of linear growth. So the more n we have, the more operations we have, nice and easy. Or we might have O of n exponential, right? N squared is usually the next exponential performance we look at. So for every n items, you have to do n things, right? If I have a list of 10 things and I want to see, hey, is there a value inside of it? I have to look at all 10 things to see if that value is inside of it. That's fine. But if I wanted to now say, hey, what is the, what's a quick exponential here? If we wanted to take the value of each one times the value of each other one. I don't know why you'd want to do that. Some sort of multiplication, right? So the first value times all the other values to come up with some sort of crazy thing, right? For every item, we'd have to do it n times. So it's n squared, it's exponential. There's other ones we'll get at real easy. Hey, have fun at work, Aiden. Thanks for coming on by. Right, that one's bad. And then we have this O of n, or really 2 to the n, 2 to the n. Sorry, that's my sugar. I'm going to have to go to the vending machine in just a minute. I want to wrap up these quick performance ones, and then I can go get some sugar. So like 2 to the n is even worse in terms of how many operations that takes. And then I believe the worst one here, and I can go Google this to make sure here, is going to be n factorial. I think n factorial is worse than 2 to the n. And we can even graph it here to see, right? So what is 2 to the x or x factorial? Wow, that gets nuts here. But one of these, we don't actually care about like any of those negative planes here, is super bad. And I want to see which one is it here. This is green is exponential, 2 to the x, and x factorial is red. Yeah, so x factorial grows even faster. Right, that is the worst one here. But most of the other ones kind of disappear off the map when we look at those. Right? I mean, 2 to the x is pretty bad, or 2 to the n. Again, I don't know why we use n instead of x. But math likes x. We like n for sequences. And x factorial is bad. So things that take up lots of time. So when we looked at that bad Fibonacci sequence, right, the bad recursive sequence, and I said, hey, Fibonacci of 50 was the sum of Fibonacci of 49 plus the sum of Fibonacci 48. Well, sum of Fibonacci 49 was the sum of Fibonacci 48 plus Fibonacci 47. That's growing factorially, right? Because 50 was going to be 49 plus 48, and 49 was 48 plus 47, and 48 was 47 plus 46. So for every one of those, I spawned off a whole other tree of other operations we had to do. The amount of operations it took was ridiculously slow, right? The number of times we had to add up 1 to get to that value was going to grow crazily here. So performance-wise, right, terms of things that are fast and slow, right? The closer you can get to constant, the better, but we can't always get there. So we're going to look at these different data structures, the ways of storing data. That's our fancy term for it, a data structure. How do we store data in memory? Right? A list is one way of storing, and how does it perform? Right? It's really nice for looking things up. So our lists then for lookups here, looking up values by index, was constant, was O of 1. Right? Because we had the index, we could just jump to it. If we had to look up a value, look up value by value, right? If I just said, hey, is there a 10 in your list? Right? There's no way about it. It was O of n. I mean, okay, sure. Maybe it was near the front of your list. Maybe it was near the back of your list. Maybe it didn't exist. So on average, sure, you could say O of half n over 2. But again, we throw away coefficients. Right? So maybe O of n over 2, but we throw away over 2. Does that make sense? Because again, maybe it's near the front and it's fast, maybe it's near the back and it's slow, maybe it doesn't exist. So on average, half, sure, but we're going to throw away the half. So it's still a linear growth. So still linear is the point here. So the more n you have, the longer it takes to find something in a list. Okay, for inserting, right? We looked at inserting. It's again, n minus the kth index wherever you're inserting, n of half, n over 2. But again, we're going to throw away the coefficients, so it's still linear, right? So it's still a linear operation. So a lot of times what we're going to look at is how fast it takes to add something, either to the end or a given index, right? And they differ, right? Adding to a list is always fast at the end, slow everywhere else, right? In terms of n, because it grows linearly instead of constant. And then looking something up by index or by value. Now, not every data structure you can look something up by index. We don't always store things by index. We're going to look at other data structures as we go and see things can be stored differently. This is not the only way to store information, but it's good for certain cases and it's bad for other cases. So if we were keeping a list and we wanted to store something or insert them by value, right, it's going to be fast or slow. So if we were to walk around campus and say, hey, I want to keep a list of people sorted by their birthday. month and day. Forget the year, just do month and day, right? It's probably pretty rare that we're going to find people in order, and I'll say, oh, you were January, great, I'll add you. Oh, you were February, let me add you. Oh, you were March, let me add you. Oh, you were April, let me add you. The chance of that was probably pretty low. So we're going to have to be moving people around as we go in that list. Oh, okay, you came before. Oh, you came after. Oh, you came in the middle, right? Most of our inserts are going to be somewhere in the middle of the list when we ask for people's birthdays. Now, I'm supposed to go get sugar. That's why I keep yelling at me. I'm sorry. We're almost done, and we can just call it for Thursday. Is that okay if we just power on for another 5 minutes? It's going to beep again really loud, but then I can go get my sugar. My mouth is starting to feel a little funny. Oh, if I break now, I'll have to drink the sugar, and I'll have to come back. We'll pick it back up. And I'm not going to pass out yet. I got a couple more minutes.
You better not.
No, I've yet to pass out in the 9 years of being a diabetic. 8 years? How long has it been? I don't even remember now. I should remember how old I was, but I don't. I've yet to pass out from having low sugar. So usually I can tell. I'm starting to get a little sweaty, so got a couple minutes. So inserting something is slow if you're inserting anywhere other than the end. So in terms of, is this going to be an issue for us? Probably not, because we're not going to run into more than like 100 people. So do we care that it takes a little bit of time if our N is relatively low? No. But if we're going to survey like all of Michigan, and we've got 10 million people, then yes, we're going to care that it's slow. So that's sort of going to be the trade-offs as we look at these data structures is we need to know the performance, and then really we need to care about, well, what really is our N population? What is the size that we're going to be looking at? So if we're doing things, even if it's slow, if we're only doing it 10 times, 100 times, we probably could care less because the computer is fast enough. But if we're doing this like with that Fibonacci thing and we're getting to the millions of operations really quickly, yeah, we're going to care to make sure it's performant. So that's when some of this stuff will matter. So array-based sequences are good at some things and bad at others. And that's what we wanted to focus on for array-based lists. We're not going to bother building our own because that's really boring. What we're going to look at when it comes to lab time is sort of how we can actually do some of these timing simulations. Now, math is always going to be more accurate. Right? If we can get the mathematical values, that's the best. Sometimes the math is hard, and maybe it's a little bit easier for us to simulate this and get, how long does it take my computer to do it here to look at some of these? Now, computers do a whole lot of things all at once. So doing those sort of runtime analysis of how long did it take my computer to run it is prone to error. So the best thing we can do is just do it a bunch of times and come up with an average. So instead of just running it one time and saying, oh, it took my computer 57 milliseconds one time to do something, we're going to do it like 1,000 times and average. Okay, well, the average might have been closer to 67 milliseconds. Sometimes it was faster, sometimes it was slower. And if your computer is busy doing something, like Windows updates behind the scenes, that run is going to be slow. So it's never very precise, but it gives us a good estimate and a good feel for, okay, on average, it took about this much time. And then if we're running on the same computer, we can kind of compare those things and see which one's fast and which one's slow. So there's a quick way we're going to look at on Thursday where we can grab the amount of time it takes to do an operation, and then I can kind of graph that out. And we'll look at it. We'll look at some of that plotting again, which was really fun to look at the speed of some of these operations. And again, most of the time we care about average performance because, yeah, the best case when you go and find something in a list is it's the very first thing. You found it with one lookup. Hey, I was looking for the number 42. It was the first value in your list. Great. Best time is not very useful, though, for saying, hey, is a list really good for looking up values by value? No, because rarely is it ever going to be your first thing, right? Often it won't even be in the list, and you'll have to have looked at n items. So average takes into account best and worst, right? And it's going to, again, average it. That's why we care about average. The worst case lookups, again, not all that useful all the time because the worst case is it wasn't in the list. You had to look at every single item. So average gives us a better feel for, and that's why mostly we'll focus on average performance. In your data structures and algorithms analysis class, if you do continue on, you'll get very much more specific and look at much more finer detail of all sorts of these things. We're going to kind of cheat a little bit and just look at averages because that's what we really care about. Occasionally I'll ask you best or worst, those sorts of things. They're good to know, but we'll focus on and what's more useful and practical is average. Okay, I think we probably got far enough. On Thursday, we'll talk about the project solution, and then we'll finish up array-based sequences. When we come to lab, we'll actually go and start doing some of those plottings. We'll like add a bunch of things to list. We'll look up a bunch of values and actually try and look at the performance and graph them here and see if we can see some of those spikes, and it's kind of fun. So just to be a little more hands-on looking at the data. All right, so I'm going to go get some sugar, and we'll just call it a day, because by the time I get my sugar and I start feeling better, it's going to be another 15 minutes anyway. So, all right, it's been fun. You guys stay safe in the snow. Don't go out if you can help it. Again, if you want to come to campus, if we're open on Thursday, I'll do my best to make it here. I live on a main road, and it's all freeways to get here. So if things are fine on Thursday, I can probably make it. If the campus is closed because things are ugly, then I'll just stream from home, and we can still talk about the things we need to on Thursday. And then by Tuesday, next Tuesday for lab, we should be hopefully all clear. All right, so let me know what I can do to help. Definitely make sure you get your projects in. I do partial points, so if you're not quite there, oh, I don't have a rubric. I thought I had the rubric posted. I will post a rubric for you, and that's how I'm going to score it. So after I get my sugar, I'll get that posted. Just come check Canvas. I'll post it later this afternoon. You can see there's like 2 points for doing this, 2 points for doing this, 2 points for doing this. So it's going to be, because we have the ship class, we have the cruiser class, we have the battleship class, we have the repair ship class, and we have the corvette class. Essentially 1 point per class for those. 1 point for ship, 1 point for battleship, 1 point for cruiser, 1 point for corvette, 1 point for repair ship, and then points for testing them. So 5 points for the ships, 5 points for testing them. So 2 points per class, essentially. 1 for doing it, 1 for making sure it works. And that'll be the 10 points here, okay? I'll post that in a little while. I gotta go get the sugar. Thanks, folks. I'll be around. Shoot me messages. Let me know what I can do to help.